So welcome everybody. My name is Renee and I'm a fourth year student at the University of Windsor, and I will be hosting today's talk by Dr. Xiao on affordable magnetic resonance from $1 million MRI to a backpack scanner. Dr. Xiao did her PhD at the University of Brunswick in 2013, and then she worked in the same group as a postdoc until 2015 and as a research scientist in 2017 when she joined the University of Windsor as a professor. Dr. Xiao, the floor is yours.
Okay, thank you very much for the introduction, Renee. This is my MRI lab at University of Windsor. We have a space at Essex Core. It's a brand new shiny lab with glass walls. We have a small animal scanner from Aspect Imaging. It's very compact if you compare it to the normal MRI in the hospital. This is type of the image we take. Only in the pandemic, I fully appreciate how great it is to have a maintenance-free instrument where I don't have to worry about magnet quenching. But this is not the magnet I'm going to talk about today because it doesn't fit into a backpack. So I will briefly introduce the background of magnetic resonance imaging and talk about relaxometry and on our recent work on deep learning-based MR data processing and some outlook of the applications with low-cost magnetic resonance scanners. So MRI is one of the most powerful imaging modality. The most significant point is there's no ionization radiation, so it's totally non-invasive, safe for a patient. It provides high resolution on the order of millimeter, usually sub-millimeter. And a very powerful part of MRI is the very rich soft tissue contrast. So these three images are the same size from a brain. And you can see that you can reverse the contrast of the image really easily just by executing different type of experiments. This won't be possible by all means with, for example, CT. And because I'm talking about low cost MR, I want to first mention the other end of the spectrum, high field MR and expensive MRI. I took this picture over a year ago in France. This is highest field human scanner. If you think about MRI on small animals with a smaller bore, people have made higher field, but for human, this has been a record. It's 11.7 Tesla. If you are not familiar with the unit of the magnetic field, 1 Tesla is about 20,000 times the Earth's magnetic field. So it's very high field, and the fringe field where we use 5 Gauss line as the safe guidance, that's 2 rooms away. This is situated in a really large building, and you don't see how large this gigantic instrument is because there's no reference. Look at the board here. Imagine you would add gradient coils and shimming coils and RF coils and then put a human inside. So you can imagine how large this is. The cost, they had budgeted for 50 million euros and they had overspent from the planning, the designing, construction, delivery to commissioning. It took more than 10 years. So this would be the goal of the vast majority of MRI researchers to have such an instrument. And let's see why they want to spend so much money on it. Back to the physics of MRI, just a brief introduction. So we are mostly interested in the hydrogen nuclei. When you put a hydrogen nuclei on a quantum, okay. So the hydrogen nuclei, each of them has a spin half, so there is a magnetic moment associated with it. You can think about these magnetic moment as each individual small magnet. When there's no external magnetic field, these magnetic moment will be randomly oriented, so there's no net magnetic moment. You don't have anything on the whole ensemble. And once you apply this external magnetic field, the energy level split, so these would become aligned either anti-parallel or parallel to the external field. So you get a net magnetization. I draw a very large vector because it looks nice this way, but it's actually a very small quantity. Here is the expression how you calculate this bulk magnetization. N is the total quantity of your spins, the number of hydrogen nuclei. And this part is just some coefficient that you cannot change once your system is set up, unless you want to decrease the temperature by freezing your patient. Here is term B naught. So that's why people want to have higher B naught to increase this bulk magnetization, so you have a higher signal. In general, this rate is really, really small. If you set B naught at 1 Tesla, and this would be only 3 parts per million. So MRI is intrinsically a very low sensitivity technique. That's the major limit on spatial resolution. If you're going to do an image with high spatial resolution, that means you have a smaller voxel, so you have even less of this N in there, so you have very small signal. And from here on, once the bulk magnetization is created, we can consider this system classically. This vector is sitting along the direction. That's the direction of the external magnetic field. And the signal cannot be detected in this way. Signal can only be detected when it's in the transverse with the XY component. So you use an oscillating magnetic field, a second field, we call that B1. It's also called RF field because it's in the radio frequency range to tip this magnetization down to the transverse, therefore to create a detectable signal. But this magnetization would want to recover back to its thermal equilibrium position. So the longitudinal component would have the exponential recovery, and transverse component would have exponential decay. If you look at when t is infinity, this term would go to 0. So yeah, mz is m naught. Here it approaches 0. What is important is these parameters T1 and T2 as the rate of either recovery or decay. We call that signal lifetimes or relaxation times. These are intrinsic parameters related to the tissue property on the microscopic level. So you can take this as the signature of your tissue, and by measuring the relaxation times, that gives you an idea of different property of the tissue. So that's where the contrast is from. The gray matter and white matter, they have different T1 and T2 relaxation times. So by changing experimental parameter, you could reverse the contrast. We call this qualitative imaging because each of the voxel intensity is a complicated function of many factors. Rho is proton density, how many the population of spins. T1 and T2 are the relaxation times we just talked about. D is sometimes involved is the diffusion coefficient. So instead of having each of the voxel as a complicated combination of these parameters, we could do better than that by doing some quantitative experiment, which means you want to have a map instead of all of these together. You can have a pure proton density map, T1 relaxation map, T2, and so on and so forth, so that you have more precise information of what you are measuring. So how do we do that? This is a simple example of measuring T2, a T2 weighted experiment. This is your signal intensity and is related to the proton density with some T2 weighting. T is the experimental parameter we could control. So both rho and T2 are unknown. So to solve the two unknowns, you need at least two equations. Therefore, you repeat the experiment twice with different parameter and solve for it. In theory, it's okay, but in practice, it's hard to do, as in inverting this, you would have noise amplification. And in the end, you get one T2 values for each of the voxel. So you get a T2 map like this. This still is the brain. For each of the voxel intensity, instead of a combination of many parameters, you just have the T2 relaxation time and put it together with respect to their spatial location. But this is not the ideal description of physical property of the brain, because if you zoom in, you can see within this very small voxel, you would have different structures of different type of cells and different component of the cells and how they are connected. So you would expect a single T2 value is some kind of average of everything inside here. And that's a very rough estimation of the real situation. So to do better, you could get a spectrum of T2. In this case, instead of one number, you have this is the T2 axis, the T2 relaxation time, and this is the intensity. So at each of the T2 values, you have a certain intensity that tells you how many different T2 components you have there. The area represents the quantity of the spin with such T2 values. And you could assign different peaks to different microscopic components, such as mining water, CSF fluid, intra and extracellular water. And this is very important in some clinical setting because the mining water content is a good indication of your neural function in the MS, multiple sclerosis disease. A lot of times before the patient shows symptoms, you could detect that the mining water content has decreased. So this has been very useful in early detection of some of the diseases. Study also show that it is correlated with schizophrenia. Okay, and this type of information is you cannot get from the qualitative imaging and even just a single average T2 with each of the voxel. So to get this, even though it takes some effort, is of some significance. Another example is if you study the skin. It has very regular structures with a few distinct components: epidermis, dermis, vessels, hypodermis. They are distinct because of their microscopic cell structures and how they are interacting microscopically of the water environment. So if you were to take a T2 spectrum measurement on the different voxels, you would probably expect for different microscopic components would have different T2 values. This is just a hypothetical result. I would expect this layer is very dry, so the T2 is probably small, and with the second layer, the T2 would be larger, so on and so forth. With the vessel, a lot of liquid, so that should correspond to high T2 values. For the individual voxel, if you do a T2 spectrum experiment, you might get this. And if you just do a bulk measurement without such high spatial resolution, that means you're summing up everything within this whole region. So you're summing up the spectrum weighted by its quantity. So I would expect something like this, where you could identify different peaks corresponding to different tissue components. So instead of when your patient coming in to examine the skin, instead of acquiring such a high resolution image, this was acquired at 3 Tesla with the huge medical scanner. You could do a relaxation spectrum experiment, try to get something like this. So that's a spot, even though it's large, but you get the sum of the different component and its relative quantities. The position of the peaks correspond to the property of the tissue. And this could be a prior information that you gathered. And your next patient coming in, if you do the experiment and get a spectrum like this, that one of the peaks has shifted, you will know that something's not right. So this is an alternative way of thinking about diagnosis using the spectrum information instead of the spatial information. Let's compare these two methods. For imaging, you have high resolution image. Relaxometry is to measure the spectrum of some relaxation parameter. The first one, it requires high magnetic field so that you could get high spatial resolution. It also requires homogeneous field to avoid image artifact. For the red one, you could have, compared to the high spatial resolution, you could measure it in a large volume to compensate for the B0, even though you don't have a lot of signal at low field. But if you could take all the signal from a large volume, that helps you boost the signal test. And you don't need very homogeneous B0 field because you have the temporal domain signal instead of analyzing the spectral domain. So this comes down to if you need an instrument like this to do such experiment, you only need something very small and very compact to do this relaxometry experiment. And these two pictures are out of proportion. If I try to scale this back at the same scale, I think it would look like that. Okay, let's take a better look at our handheld MR scanner. It has low field, 0.1 Tesla, has a small sensitive spot. You cannot fit the whole human body inside. It has highly inhomogeneous static magnetic field, has highly inhomogeneous radio frequency magnetic field. So why do we want that? Because it's really, really cheap. So imagine we each could have one of these things at home and just do measurement as we wish, because the cost is really minimal compared to the 15 million euro scanner. And this is not only restricted to a spot measurement, because you could do mechanical scanning. You could have one spot and then move it to the next spot. So there you have some spatial information involved. And you could even do something like a super resolution, move it instead of one space, you move it half so that you can figure out in a finer scale. So you can still get a lot of it. The measurement sounds great. And now let's see how we get the information from the measurements. This is universal in most of the experiments. You would have some measure data, I use S, and some information that's related to your measurement by some encoding matrix. And we'll take data. You want to get A from this measured S. So the goal is to how you interpret your data. And it's universal in many different places. Let's look at what the signal equation is for the imaging case. We write our acquired signal as the sum of here, A is the image, is a function of spatial position. Each position is weighted by a phase term. So if you discretize this expression, you can see that this is just the Fourier matrix when you sample all the data according to the Nyquist criteria. So the square matrix is unitary. This is wonderfully simple because to get from S to A is just a simple inverse Fourier transform, where you take the Hermitian conjugate of your Fourier matrix. And things are not always so great. If you want to scan your patient faster, so you don't take all the data points, you skip some. Therefore, your signal equation is undersampled Fourier matrix, where you have more number of unknowns compared to the number of number of equations. So it's an underdetermined system. You can no longer have that simple solution of getting an image. So this is my student Mark Armstrong's solution how to solve that equation. It's very readable here. So he has the idea is you would have to use something way more complicated than a simple inverse Fourier transform. This is part of this is his undergraduate thesis work. He's now a graduate student in our group. And he has applied this method with some very clever undersampling scheme in vivo experiment. So this is the application of some cell tracking experiment where some immune cells are tagged with contrast agents, and how they move inside the mouse brain will give you insights in some inflammatory disease in collaboration with our preclinical partner, Germany. And with this undersampling, he could increase the temporal resolution. Instead of taking minutes to acquire this image, where these fast-moving cells are blurred out, you don't observe it, he could get this detection limit improved by almost an order of magnitude. And in this experiment, he has acquired a fully sampled and undersampled simultaneously, so he could compare the result. This is one way of one example of signal equation and how you solve it. Another example from Leo, she's a graduate student from our group. She has incorporated more information in this A factor. Instead of just image, she has incorporated the field distribution, especially in the extreme case where you have a severe magnetic field distortion from metal implant. This is a very challenging situation in a conventional way because that leads to severe imaging artifact. But she could actually measure it by rearranging these equations and do experiment in unconventional way. Okay, let's come back to our signal equation for relaxometry. In this case, we have exponential decay. Our signal as a function of time is the T2 weighting factor here. And for each of the T2 component, we have an amplitude. The goal is to solve for this A given the measurement S. So that's your spectrum. And this is the so-called inverse Laplace transform. Is a notoriously hard problem to solve because it's ill-posed. This kernel of integration it does have vanishing singular values, so you cannot easily invert this. What that means is the solutions are not unique, and a small perturbation within your measured signal could lead to very large fluctuations in your spectrum. So it's a challenge, and the traditional method that requires, usually what people do is you would acquire numerous data points, high quality data points with good SNR, and that means you would have lengthy measurement time. And this problem is not unique to our system. In a lot of other physics problems, they need to solve the same equation. So traditional solution is to incorporate some prior knowledge of the spectrum you're trying to solve. The most common ones are the negativity constraint, which says you should not have negative spectrum amplitude. And sometimes people make some further assumption that you only have a few discrete components, not more than 3 usually. Also, you can impose how smooth or how sparse your spectrum is. Mathematically, that would be an optimization problem with some either L1 norm or L2 norm constraint. And the solution is very largely dependent on this regularization parameter that is here. With the constraint, you want to balance your data consistency and how hard you impose this smoothness or sparsity. This is the result from the usual L2 norm solution. The shape of the spectrum, this is our A, largely depend on this parameter, and this is a user-defined parameter. So when I run this code, the inverse Laplace transform, I could set the parameter as I like, and I would get different solutions. In general, if you set it high, you will get spectrum peak that's wider. If you set it low, you get narrow peaks. That's similar to improve the resolution of the spectrum, but it usually results in spurious peaks. And also very importantly, the performance is largely SNR dependent. If you take a very low signal to noise ratio data and you get something very unstable. So we have, without the deep learning is so powerful, we have seen so many applications of it. In the MRI society, it's mostly used for the image segmentation and classification. It has also been used for image reconstruction. And we have seen the automatic self-driving car, voice recognition, the Siri. Playing chess, solving Schrodinger equations is so powerful, it can do so many things. So we thought maybe we should try to use that to solve our signal equations. Here is a brief introduction on deep learning, artificial neural network. It's from the biological neurons and neural networks. So all the neurons are interconnected with some channel, and the signals are passed by some electric signal. The information is transmitted through the electric signal. So you would have one layer of neuron, and then they are all connected to the next layer by some channels. Mathematically, it could be expressed as the signal coming in and weighted by some coefficients. After they are summed, they go through some nonlinear activation function. In this example, the activation function is just a simple threshold. So what this means is not like if you have little signal coming in, this is activated a little bit. It only is the next layer of neuron is only activated once this accumulated electric signal is passing some threshold. So that's the nonlinear part of artificial neural networks. That's what makes it so powerful to solving these nonlinear problems. In general, artificial neural networks refers to fully connected networks, which means the nodes are all fully connected to the nodes in the next layer. You would have many layers, input one and some hidden ones that you don't generally see, and an output layer. And the information coming in, so that would be, in our case, the signal we acquired in the experiment, and output layer we wanted to give us the spectrum. Let's see how it works. With the input, All these coefficients of the signal is put into the different positions. They are connected through some calculations, each multiplied by its corresponding coefficient. Then I get something. The sum would go through this activation function. In the previous example is just a threshold, but this could be different shapes. And actually that is one of the very popular research topic in the deep learning society. What kind of activation function works best? So through this nonlinear function, you get some new coefficient and you put it in this node. And then you do that again. Of course, these coefficients will be different. And fill in the next node, so on and so forth. Once this layer is populated, you do the same operation to go to the next layer, and so forth until you reach the output. So once you have your neural networks, everything is forward operation. It's just a forward matrix multiplication, which is really simple. That's why it's so fast. But how do you get the network at the first place? You have to have one that works for your problem. So you train a network to make it learn to adapt to the problem you want to solve. Basically, you want the network to figure out the connection of the input and output through these coefficients and functions. So it's learning, the network is trained through back propagation instead of going from left to the right, is going from the output to the input. Basically, you give it an example input, and through some randomized coefficients at the beginning, you would have some output, and you compare these output to the real output, which is the training data set. Any discrepancy will be back propagated to change all of these coefficients so that this output will be closer to what you want. And so on and so forth. It goes back to different layers to change all of these coefficients. And then adjust itself. And then the next training data set, the next training data comes in, you do this again until after a large data set, it reaches some convergence and could properly predict what your output is given a certain input. So that's the steps of getting a neural network. Just as described. So with the training data set, it compares the output to the input, and then the arrow would be back propagated to update the different weightings and activation functions and repeat this process. So the training data set is very, very important because you want a network to know what is happening in between your input and output. You have to have the data that teaches it how to do it represent your real situation, including the noise characteristics. So with all the traditional solution where you do the L2 norm type of is the least square sense of solution, where you just assume the noise is Gaussian. But it's not really true. In this T2 experiment, we use magnitude data. You would have Gaussian noise on a real and imaginary channel separately and correlated, and the noise and the signal would be the magnitude of it. This is called ratio noise. And when your signal to noise ratio is low, this noise would deviate from Gaussian noise a lot. It's very important that you include this characteristic in your training data set so that your network knows what to do. In the traditional solution, it's really hard to deal with because you cannot predict. You cannot give it a certain part of deviation that you define. So here's an example solution, a test with simulation. The epsilon is low in here, 40, with a 2-component T2 relaxation times. On the semi-log scale, you're supposed to see a 2 two separate pieces of straight line, each indicate one T2 component. And this black dotted curve is the true signal. When you add the Ricci noise at this low SNR, because it's the amplitude, so the signal will not be deviating around your true signal, it will be elevated. And in the traditional nonlinear least square fitting solution, where you just try to predict a curve that minimizes at least the solution would go through the noise, which is largely deviated from your true signal. But with a network that's trained based on the Ricci noise model, it knows to look out for this and predict a decay curve that's remarkably similar, close to the true signal. That's why the performance could be better, is better than the traditional solution. So this result and all the other network-related results are produced by Crystal as his outstanding scholars project. He's now a graduate student in our group. And the details of these results can be found in this paper. It should come up very soon. Another very controversial issue with the spectrum analysis is if you could actually detect the peak width. So he did some simulation with a different width of the spectrum peak, and you can see that the signal actually is distinguishable as long as your noise isn't too high. So this suggests that within the SNR limit, the spectrum could be very well defined, and the peak width information could be very useful, indicating what is really going on within your sample, other than this peak width being artificially defined with a user-defined parameter. So he has done a lot of evaluations with the different parameter range. The conclusion is it could produce the accurate result. And we applied it in a phantom experiment. So we artificially created some T2 distribution phantom with discrete components representing different peak width. So for example, the blue one is made up of 3 components that has these 3 T2 values on the log scale as their position. So they represent a narrow peak, and the blue curve is the result from the network. It agrees very well with the truth. And in addition to that, so for example, this green phantom, we have more components close together in this range, and the shape of the solution reflect that by having a higher signal intensity in this part. So we are very pleased that this works, giving sensible results. He did lots of evaluations over large parameter range, including varying the peak positions, varying the peak intensities, because you can imagine if you have 2 peaks, they are of the same amplitude, it will be easier to distinguish. If one of them is very small, it will be harder. We don't have to go through the details of this, but these are the error maps under different conditions. And we compare this ANN error map with the ILT, the traditional solution in all the cases, this produce much lower error. And of course, your result would be related to your SNR. When you have higher noise, the performance of both methods would decrease. See the color bar limit at these two. But this still ANN performs better than ILT, and is just an intrinsic limit of the problem instead of the inversion method. When you have higher noise, some information are just lost. To show this, there are some simulations. This is one decay, the same signal, with ADSNR, we have 3 realizations of the noise. So they're different due to the random nature of the noise. And if you look at the beginning of the decay curve, some appears decaying faster, some appears decaying slow. That means the smaller T2 component would be shifted either to the left or to the right. So in this case, the information is just not there. It's not the limitation of your inversion. And there will be intrinsic limitation on the resolution. I will just skip this. This is another phantom experiment to show compare the performance of the inversion. We have a gel which has a T2 that's decent, moderate at 250 milliseconds. And in contact with that, there is some copper sulfate solution. This solution makes T2 shorter. So the higher concentration of copper sulfate, the smaller T2 you would have. And they are just left there, T2 measured, and monitor this system. With time, some of the copper sulfate would migrate into the gel so that the concentration of copper sulfate would decrease. And here you would have more copper sulfate, which means you have a lower T2 on the left side. And also the quantity of these two materials will change with time as well. So we did the measurement until they became totally homogeneous through many hours. And the T2, we did the same T2 experiment, just processed the data in 2 different ways. And you can see that the ANN results on the left describe the process very well. You have 2 peaks to start with, and then they both move, either both position and the quantity of the 2 peaks changed. So the small component will move to the right because the T2 concentration has decreased, and the large component moved to the left because you have more copper sulfate in the gel. And eventually they merge and the quantity change as expected. So this is a controlled experiment to verify our method with experimental data. And compared to the ILT, similar qualitatively similar results are acquired, but the transition is not as smooth as the other one. So we claim that this one is better than the ILT. The deep learning artificial network is not a silver bullet by all means, because as shown that it's still limited by the signal to noise ratio. And the training data set is very important because the network works as an interpolator. If you give it something that it had never seen before, it's not going to give you good results. It's not good at extrapolation. And in training the network, there could be overfitting problems and local minimum. There are a lot to watch out. But the advantages are significant as well because it provides fast computation speed once the network is trained, and you don't have any extra user-defined parameter. You can incorporate the noise characteristics and other primary information of your spectrum. For example, if you know some special system that has a spectrum shape of triangle, you could do that, and the output would be triangle. So that's very convenient to incorporate prior information. Also, very easy to modify the signal equation, because all we need is the training data set going simulated with the forward calculation. So you could very easily incorporate other conditions, such as the magnetic field inhomogeneity. With that small magnet, we have said the field is very inhomogeneous. Jean-Marc, as his undergraduate project, he built this 3D mapper with Arduino controller to map the magnetic field of the magnet. So he built this from scratch and reduced the cost by a factor of 10 about. And more importantly, he had lots of fun putting this together. So he mapped the field. This is what the magnetic field looks like. It's nowhere homogeneous. So in addition to the spherical hull we had, where ideal condition is considered, next step would be to incorporate all of these. And not only just the static magnetic field that's defined by the magnet, we could modify the field by incorporating extra coils. This is Jordan's work. She's an undergraduate student now. So you could make some DC coils to put direct current in it to generate extra magnetic field and put it on top of your existing field to modify it to get a better condition. It's not limited by all means of what you could do. You could have a coil made this shape, or you could make it like this shape. So she has a way of going from the field to the coil geometry so that whatever you want, she could make it for you. This is on the B0 static field side. In addition to that, we have a problem with the radio frequency field. So that's the B1. This is Doris' project. She's still working in our group. She started as a USRA this past summer. She's designing different type of coils to optimize signal-to-noise ratio, but also optimize the B1 field to match our small magnets. So that, well, by changing these, you are actually changing this encoding matrix. So we said no matter what kind of inversion problem you have, if you have degeneracy within your signal, you're not going to reliably solve for the information. So another way to consider is change this encoding matrix to something that's much easier to invert or have a better distinction between different type of informations. And this type of relaxometry is not limited to 1D T2 spectrum. You could have T1, T2 correlation. So instead of just T2, you add T1 into a different dimension where you have a better idea of the tissue property. In addition to that, you could add in diffusion because magnetic resonance is very sensitive to motion. With diffusion in anisotropic microscopic environment, you would have different diffusion coefficient in different directions. That means this could expand to a very large encoding space. Okay, so in the end, I'd like to mention a few non-medical applications. This is actually Alex's idea. She worked in my group as an undergraduate student. I gave students lots of freedom in exploring their own ideas. And she found this disease in tomato, which I cannot pronounce. So this is already in the late stage where you could see the disease. But in the early stage, this fungal infection would happen without being visible, but it would transmit to other tomatoes. And we think by analyzing the relaxation spectrum, we should be able to detect this tissue change in the early stage before it's visible. So the long-term goal would be to have tomato instead of in lab on the vine and have this portable scanner to bring it to the field to survey how healthy your crops. And this project got more serious recently in collaboration with the Ontario Greenhouse Vegetable Growers. They are a non-profit organization, represents more than 200 growers. So we got some funding from them in pursuing this. Another application, I should give credit to the pandemic for this one. Being isolated at home, I started a new hobby in building a garden. So I grew lots of vegetables, and including tomatoes. And I wanted to grow the best tomatoes, so I did some homework in studying the plant physiology. And I also talked to a professor in the School of Environment who is the expert of plant roots. Asked him lots of questions. Well, I learned that the interaction of soil and roots are a very complicated process. At the same time of the water and nutrient uptake, the root would excudate, so it's a two-way process. I asked him lots of questions. Surprisingly, he couldn't answer them all. For example, there is this 4R principle in fertilizer application. It says right source, right place, right rate, right time. So I asked him, what does that mean? I need something more quantitative than just right. He said people don't really know. So there are many different theories, but nobody really, there's no actual technique that gives you real-time measurement of this process non-invasively. So I thought, okay, maybe I could measure it. So I could have a small magnet in the soil to, again, I have to sacrifice the spatial information with the functional information. If I could, in real time, measure the interaction of the root soil, I may be able to answer these questions better myself. And this type of magnet exists commercially, so you could just buy these. They are very low cost. So that's another very exciting application we are working on. So in the end, I like to acknowledge my students. All of these exciting projects are possible due to their great work. And also I'd like to acknowledge my funding agencies. Thank you for your attention.
Open for questions now. You guys can put them in the chat or unmute yourselves and ask.
How can I see people's? Okay.
You might have to stop sharing.
Okay. Yeah, I think so.
While we're waiting for other questions, I have a question for you. So you talked about the deep learning around slide 30-ish. And it seems to me that the main application for your research group is in the artificial neural networks. Do you guys use this deep learning for anything else in your research, or is that primarily?
Well, it's it's a good question. There are a lot of ways we can use it. So far, that's for data processing, where you go from the acquired signal back to the information space, which is a really hard problem in a traditional sense. Also, at the end, I mentioned that you could modify your encoding matrix by having different type of magnetic field. So that's a really large parameter space, how you design the new experiment. I think there is potential in using deep learning to optimize your experimental design, to come up with the best strategy of your encoding matrix E so that your information is best captured at the first place. Yeah, and also there are a lot of, yeah, that's the general idea. I will stop from there.
Okay, thank you. Any other questions?
I have several actually. that was fantastic, Dan. That was really really good. I like that a lot.
Thank you.
So I have some that could maybe stimulate questions from other people. One was a physics question. So just on slide 12, which we're not looking at now, but you showed it was a T2 spectrum of all those different peaks. Just for the physics, is there anything other than the quantity of spins that affects that area under the curve of those T2 peaks? You said it was just the number of spins, but is there more physics to that than that?
Oh, the physics part is not in the quantity of the spin, it's in the T2 values.
Okay.
So the T2 value is an indication of microscopic interaction environment of the nuclei. So for example, if you take butter versus oil, you have solid versus liquid. So in the liquid, you would have the spin tangling around. So that's the dipole-dipole interaction is average. Therefore, you have a long T2. And in the solid, because the matrix is rigid, so the interaction of how this energy is lost is very different from the liquid sense. Therefore, you have short T2. So the T2 values are the indication of the physics, and the area underneath the spectrum peak is the quantity. Of course, this is a very simplified picture where you have two things, and then you may have two things that's interacting with each other. So that gives you the T2. Yeah, interpreting the relaxation times is a very difficult physics problem, and the people do have theoretical calculations. Like I've talked to Dr. Kim before, and he I think he showed me papers on how those how T2 is calculated from the quantum mechanical point of view, but people only do that for the very pure material. You cannot do it really in the skin or in the tissue because it's so there are so many things. If you write out the Hamiltonian, it's going to drive you crazy. Yeah, I think. Yeah. So people have very positive explanations on high T2, low T2, but I don't think people would really rigorously calculate it in a complicated situation. In a pure material like copper sulfate or something, just one type of material where you have the lattice that's really regular, where you could.
Yep. So on an imaging question on slide 14, maybe if you could show slide 14, that might be helpful.
Okay.
I just have a question about a general medical imaging question that I'm wondering if you could help me as I explain it to other people, because I don't know the answer.
Okay.
I'll let you bring that up.
Slide 14. Okay.
Yep, it's coming. Okay, here we go. Yep, yep, that's fine. 14 or even or maybe the one of the ones before that has a zoomed in image of that MR. Yeah, like this one, where that picture is big. What would you what exactly, how would you estimate the spatial resolution of that picture? I see the millimeter scale at the bottom, and you certainly have structures outlined like that one vessel, the top vessel at V, that looks to be about a millimeter or roughly. Do you have a way in MRI, if you look at this image, what is the spatial resolution of this image? Is it a millimeter? Is it half a millimeter? Or do you have some quantitative way that you quantify that in your field?
Well, there is a very simple parameter. I call that nominal spatial resolution, which is just a voxel size.
Okay.
If you think about this structure that's made up of many small voxels, and you count the size of that voxel, that's kind of an indication of the spatial resolution. But that's not the real spatial resolution, because I'm very sure that this image has been interpolated.
Oh. Okay.
Yeah, so the true resolution would be considering your points per function and considering all of the other factors. So we if you think about current data in the k-space, so k-max is a good indication of your resolution. How far you go in k-space, like what is the highest frequency of data you sample. But again, that's not really true, because you might have some modulation transfer function due to your T2 star decay, T2 decay. So you have something on top of that. That's another layer of convolution. And also when you truncate a K-space and do the Fourier transform, that's a convolution with a sinc function. So that's another convolution. So we use the full width half maximum of all of these of the total convolution kernel to indicate your resolution in addition to your voxel size.
Okay, perfect. Thank you. That's actually an excellent answer. So it's very mathematical. I mean, I think the bottom line, I'm just trying to think how do I explain it to a second year student, is that to look at the picture, you can't really do it, right? Everything you just said is not really in that picture. They don't have the point spread function in that picture. And I mean, the voxel is in that picture, I guess. You can kind of see that, but it is complicated.
Yeah, you can see the voxel size, but you can also show two images side by side. One is just a raw voxel, the other is being interpolated. You could see that interpolated version has apparent resolution that's higher, that looks smoother, looks nicer, but that's not real higher resolution image.
Okay, great. I had a question about what was the object in slide 23? Maybe I missed that somehow.
20. Oh, okay.
Yes.
I'm not going into too much detail.
What is that?
That's a mouse brain.
Oh, okay. All right. It's okay.
That's a slice of a mouse brain. So this experiment, they inject the immune cells being tagged by contrast agent into the mouse, and they wait a while and see how these immune cells distribute and going through their system, how much, and in the brain, in which part, how fast they flow. I don't have any real idea on the medical background, but I know they say that this is really important for them to understand some disease, how the blood vessel and these cells travel.
Okay.
Yeah.
That's really cool. That's really cool.
Yeah, the cool part is this is the normal image they would have acquired, but Mark's work make these extra dots visible.
Absolutely.
Yeah.
That is cool. Okay, I had just one last question then. If you go to slide 47, which was the cuprate agar diffusion analysis, I believe.
Yes.
How did you, when you were trying to train the neural networks, how did you know what the correct answer was for those diffusions? Because you always do need to have a training set and know the right answer. So how did you actually train this network?
Oh, the network was pre-trained. So this is only application of, we have the network already, and we use this experimental data to test if the network performs as we expected. So the network was acquired way before.
Okay.
Yeah, okay. I think I have some backup slides about more details. So these are the activation function here. Here is the training of the network.
Okay.
He would generate, I think he has 400,000 data sets of this T2 decay curves, and he simulated them based on the different dynamic ranges and parameter space and the noise characteristics. And he used all of those data sets and put them into this procedure of training a network here.
But was that data was calculated? Like it's
was simulated.
But those were actual real agar phantoms that you were imaging?
No. This is only one agar phantom. So this is after the network is produced, and we say, okay, this is the technique to process the data. Let's test if it really works with experimental data. So we made the other experiment. This is only a test set. It has nothing to do with the training of the network, because it's a well-controlled experiment. We know what to expect in the T2 spectrum. If you just take a piece of tissue or something, you don't know what the T2 really might be. But in this situation, we could very well expect what the T2 values are based on the concentration and the the quantity of the two different populations. So we could say if the results make sense or not.
See, okay.
Yeah.
So but just to be clear, that was one phantom that you made then, just an agar group break phantom. Okay.
Yeah.
Got it.
Well, other people have raised the question like, when you train a network, why do you use simulation data instead of using real experimental data?
I guess that's what I was getting at. I mean, I thought you were making multiple phantoms, and then how did you know what the mixtures actually were?
Yeah, that's one problem. The other is we're not going to be able to make 400,000 phantoms to do the experiment with.
No.
Yeah.
Right. Okay. Yeah, unless you have 400,000 undergraduates who want to join your group, and each one of them can make a phantom and make some curves.
Oh, we don't have that much instrument time.
Oh, okay. Well, then forget that. All right. Thank you.
Thank you.
Are there any more questions? If not, thank you everyone for coming. And next week, I believe we have a talk by Dr. Markard. Same time, if you guys want to stop by. Thank you very much, Dr. Xiao.
Thank you, Renee. Have a great